Okay, I start recording the class. And let me share the screen. Okay, I hope you can see my slide. Okay, today's topic is the introduction to mechanical vibration. Actually, it's the intro to our class, but I already give some introduction in the course syllabus. But as I mentioned, we still didn't see any picture, and maybe you still don't clear in some point. So in today's class, at the end of the class, I hope all of us can answer this question. What is vibration, and how can we analyze the engineering problem with the mathematical modeling, and how to count the number of degree of freedom of mechanical system, and how can we classify the types of vibration. And we have a brief review so that after today's class, if you feel that you still not clear in some concept, you will spend your time to review by yourself about the simple harmonics, the kinematics and kinetics, and review about the work and energy concept. So in the brief review today, we will show some example to give motivation, but you need to take your time to review it by yourself. And of course, we are going to maybe spend a week or more than a week to try to obtain the equation of motion of system. Easy system, complicated system, we're going to apply the Newton's second law of motion to obtain the equation of motion. But today, we're going to give some easy example so that you can get the idea about what is the equation of motion. And vibration. What is vibration? Let's see this video first. They have a good explanation for the vibration of system. The oscillation about an equilibrium position. Vibration is the oscillation of a system about an equilibrium position. Oscillation of what? Oscillation of inertia element. So if we don't have inertia, maybe vibration has no meaning. If you only have spring, but don't have the mass in the system, the spring without mass is nothing. The vibration will have meaning if we have the inertia property in the system. If you see this video, before you see this video, we have another bullet. The mass need to deviate from the equilibrium point, and we need to have restoring force that try to pull the inertia back to the equilibrium. And the force that pull the inertia back to equilibrium is generated from the energy storage element. Energy storage element can be a kind of mechanical spring that made from spring steel, or it can be a kind of elastic things like rubber band or something like that. So another way, if we are not talking about the spring or elastic component, the gravity that try to pull the pendulum back to the equilibrium point, the gravity is a kind of potential energy storage things also. So potential energy can be gravitational potential energy and the elastic potential energy. So we see this video again. Do we have the component of the vibration system in this video? Can you see the inertia in this vibration system? Can you see the inertia? The endpoint here made of multiple pieces of aluminum, and it has mass, and of course it's inertia of the system. In this video, I think you still cannot see what is the elastic component that try to make the inertia vibrate. But the schematic for this is actually we have a leaf spring. In today's lecture, you will have a more clear, you will see many examples for this leaf spring system. I developed one, I think I should show the video. Wait a second. I have one video for you. Okay, do you see the video? In this video, I developed one system that can vary the stiffness of the system. So I adjust the length of the spring. I adjust the length of the leaf spring so that we can change the stiffness of the leaf spring. Oh, Panit, you still cannot see the video, right?
No.
How about the other guys? Can you see the video?
Yes, we can,ครับ.
Okay, Panit, unlucky. Why you cannot see my video?
Oh, it's my Zoom. I fixed it.
Okay. Don't worry, Panit. Although you cannot see the video, in the next slide, you will see the picture that describes this system again. So, okay, see the video. Okay, in this system, what we can see is we have the vertical ball screw system that drive the system up and down. We have the ball screw system that drive the system up and down. And we have another leaf screw system that drive horizontally. The leaf screw system that lies on the horizontal plane have the small motor to drive the leaf screw. When the leaf screw rotates, it will drive the position of the rollers to the left-hand side and to the right-hand side. And the important part of this system is the elastic component. The elastic component is the leaf spring. The leaf spring. If you see my finger, I touch the robot at the end point, at the inertia, at the end point, and the end point connect to one horizontal plate. That plate is made from the spring steel sheet, and we select the stiffness for the spring steel sheet, and we can model the stiffness at the endpoint. If you see the brown one that connect to maybe 5 cable near the endpoint, that one is the linear encoder. The linear encoder. If you see the clear sheet in the vertical plane, the linear encoder, the brown one, when we apply force at the endpoint, we will create the deformation. When we create the deformation at the endpoint, we will have the relative translation between the brown encoder reader and the clear plastic that have scale on it. And the linear encoder will read the deformation. And we put the control system to control the motor, to drive the roller, to compensate the diffraction at the endpoint. It means that when the roller stays far from the endpoint position, imagine that you hold a ruler by your left hand. When you hold a ruler on your left hand and you use your right hand to push down on the end tip of the rulers, if the ruler is long, you can easily bend the ruler. But when you move the support position close to the applied force position, the stiffness at the endpoint will increase. So what we do here is we try to limit the deformation at the endpoint. If the ruler stays far from the endpoint, the feeling of human that touch the robot at the endpoint, the human can feel the robot is very soft. We can use a small magnitude of force to make the spring deform. But when the robot can sense that now the deformation is too high, it will change the position of the roller support to be closer to the endpoint to increase the stiffness at the endpoint. So here is the system. And in the video, in the slide, we only see the vibration at the endpoint that generated by the leaf spring system. So we come back to here. So when we come back to here, in this system, of course, we have the inertia element, and the potential energy stored is the leaf spring here. The leaf spring. You may be familiar with the spring, the coil spring, and mass. But in this system, the spring is a leaf spring, and the mass is the thing that attached to the endpoint. And how about this? We need to study about the vibration. We need to learn this class because we want to understand the physical phenomena, understand about what is the cause of vibration, what is the parameter that affect the characteristic of the vibration system. We need to understand. So why we need to understand? In this video, maybe we may not like the sound that generated by the tool, the cutting tools, hitting the aluminum block material. So when we learn about the vibration system and we understand the characteristic of the system, we can select the suitable cutting speed and feed rate so that we can reduce the effect of the vibration, the unsatisfied vibration, to increase the lifetime of the cutting tool, or to support the, try to improve the cutting quality at the surface of the material. We need to understand the phenomena first, and then we have a tool to try to modify the vibration system so that it's gonna have the satisfied behavior. So yeah, in the real world application, sometimes we have the phenomena that we don't like the characteristic of that phenomena. For example, we have the failure in the structure. If we have some vibration system and it store energy and it increase the amount of energy that's stored in the elastic component, finally it over the limit and it break. Here is the first important thing to prevent the damage from the too much energy stored in the system. We need to try to find a way how to dissipate the energy from the system so that the structure still like not failure. And another reason is many times in our daily life activity that have the vibration problem, we feel discomfort by the physical motion or by the noise from the vibration. The problem that relate to your study in the automotive engineering field, maybe the two major problem in the automotive engineering field are the engine vibration and the vibration in the suspension system. For the engine vibration, in the beginning of the class, I tried to draw a schematic to describe the unbalanced mass in the engine. And I mentioned that at the engine mount, engineer need to decide the suitable stiffness and damping coefficient so that we can isolate the vibration from the engine that's gonna transfer to the chassis and the passenger. And another source of vibration problem in the automotive application is the road excitation. I also already draw a schematic of the sinusoidal road excitation and give some introduction that if we consider the problem in the frequency domain, maybe we can design a good suspension that can minimize the road excitation that affect the passenger. When we drive the car on the road, maybe the bump on the road may have 5 centimeter height. You drive your car on the road and you hit a speed bump, maybe the speed bump maybe have a height of 5 centimeter, but you sit on the seat in the passenger room. The vertical excitation from the road 5 centimeter don't need to be transferred to your seat. Many times, if you drive with some certain speed, you cannot even feel that 5 centimeter obstacle on the road. If the engineer can like fine tune the spring stiffness and damper for the operating speed of your car. So this is example. And in this class, you will know the technique. You will know the technique that you can design the suspension system. For example, if you know that the road excitation, the wave on the road has the magnitude of, for example, 5 centimeters, and you need to drive your car at 80 kilometers per hour. How can we isolate that vibration that's gonna affect the passenger feeling? In this class, we will learn the technique to deal with this problem. And from actual system have a lot of components in the system. We need to model it physically, model the system physically. In the process of model the system physically, the important thing is make it simple. Try to apply the assumption to make the physical system to be simple. For example, let me think about the example. If we go back to the system that I show, that we have the roller that drive to change the position of the support position, to change the stiffness at the end point, I need to assume a lot on this system. I need to assume the roller and the beam as cantilever beam with ideal cantilever support. The beam need to be cantilever beam, and at the support position, it need to be cantilever support. But of course, in the real system, I will show you the picture that at this point, it's not the ideal cantilever. For the system that you have, the spring and the mass. The spring and the mass. The mass may be 10 kilograms. The spring have the stiffness, and the spring itself also have the mass, but it may be 0.1 kilogram. In our study, we always neglect the mass of the spring. We only focus on the significant mass of the inertia component in the system. The stiffness of the spring, we always consider is constant, but in the actual spring, we can see the linear relationship between the force and the displacement just only in the beginning. After that, we can see something change, but many times we only consider the spring with a constant stiffness. Or maybe we are going to design the mechanical system that use the spring. We need to try to limit the operation range of the spring to be in the linear region. But in the real world system, spring don't need to be constant stiffness. But to make the system easy, make the system simple, we consider only the mass of the inertia component. We neglect the mass of the spring. We assume constant stiffness spring. We also neglect the friction. We also neglect the friction. This process that we try to neglect the unimportant thing from the actual system to be the physical model is called physical modeling. We try to consider only important thing in the system and neglect the unimportant thing. And after we have the physical model that have only mass and spring, the next step that we're gonna have the equation of motion. How can we obtain the equation of motion? This process is mathematical modeling. We need to apply physical laws. It may be Newton's law of motion or work and energy theory to obtain the math model that describes the system motion. And when we have the equation of motion, we can predict the vibration of the system. We can predict the vibration of the system. If we can predict it, we can just like compare it to the actual vibration. We have the actual system. We try to do some experiment and we compare the result from the experiment to the one that we can predict from the model, compare. Or if we know the characteristic of the system and we don't like it, we need to improve the characteristic of the system. For example, the current automobile system, we have current damping and stiffness, but we don't like it. How can we tune the stiffness and the damper so that we can have better characteristic of the suspension? It's on this part. So yeah, as I mentioned, from the problem, any physical problem, we need to identify the problem first. What are the known constant in the problem? What are the unknown parameter or variable? Again, we come back to the most simple one, this one. We have mass, we have spring. Can we measure the mass? Can we measure the spring stiffness? If we can, M and K need to be the constant that we know from the problem. The unknown or the variable in the system may be the displacement that varying against time. We need to, it can be changed against time. We need to find a technique to measure or estimate the displacement. And again, about the assumption, various assumptions to the system. I already mentioned that sometimes we need to neglect the mass of the spring. We need to neglect the mass of the spring. Sometimes we need to apply the small angle assumption so that we can estimate the sine cosine function of the angle. Sometimes we need to assume the small angle. Sometimes we need to assume the small deformation. Assume the small deformation come from here. At one region, the spring is linear spring. Have the linear relationship between the force and the displacement, but at bigger region of the deformation, sometimes it's not linear spring anymore. So yeah, in the system, we need to see, should we assume small deformation? Should we neglect the mass of the structure? Should we assume the small angle or constant stiffness? Here, when I show the video, there is one of our friends who cannot see the video. So these three images gonna explain what you missed from the video. In the video, I show the system that have the vertical ball screw system that drive the things up and down. And we have another motor, this motor, that drive this screw. When the screw rotates, we're gonna change the position of the roller to the left and to the right. At the end point of the system, we apply the force here. We apply the force, and the leaf spring has the deformation. The stiffness is the force divided by the deformation. If the beam, the leaf spring, if the leaf spring is a cantilever leaf spring, ideal cantilever leaf spring, the stiffness K can be assumed, can be approximate from the Young modulus of the material, the second moment of area of the material, and the length L, the length L between the applied force position and the cantilever support, the length L. So in this concept, what we can see is we can adjust the length L. If we change the roller position close to the end point, we're gonna decrease the length L, isn't it? If we decrease the length L, do you think we're gonna have bigger or smaller stiffness? Smaller L, big or small stiffness?
Big.
Yes, thank you. So if you see here, if L is more, L power 3, we're gonna have big stiffness. Does that make sense? Does that make sense? I'm not sure if I have a ruler here. Maybe this one. Okay, this one is like a foam sheet. So if the support, the cantilever support is far from the endpoint, we can make it bend like this, right? We apply 1 magnitude of force, and with the small stiffness, it bend with big deformation. But if I change the position of the support to here, and I try to apply the force, I need more force if I still require the equal amount of the deformation. So when the support is close to the endpoint, the stiffness at the endpoint increase. So here is the concept. And but unlucky, the actual system is not ideal cantilever support. When we have the left pair roller, when we have a right pair roller, and we have a spring material, for the ideal cantilever support, for the ideal cantilever, at this point, it needs to be 90 degrees. But in the real system, we realize that we can see the spring bend between the left pair and the right pair of roller. The roller can support the zero vertical displacement. The roller can block the position. The roller can block the position, but it cannot block the slope. The roller can block the position. The displacement, the vertical displacement at the roller support point is 0, but the slope don't need to be 0. But for the ideal cantilever support, the displacement need to be 0. The slope need to be 0. So in our case, in our example here in this system, we cannot assume the ideal cantilever support. And the last concept before we continue is about the free body diagram. Today we will review about the free body diagram, but free body diagram need to relate the body that we separate from the whole system and show the body and the surrounding of the body in the form of force. For example, you have the spring and the mass. You have the spring and the mass, and you draw the free body diagram of the mass. You are not going to draw the spring anymore, but the effect of the surrounding need to be represented by the form of force. The force by the spring instead. And the concept of the body force and surface force, the concept of the body force and surface force, again, if I don't like that, I don't have the space to draw. Again, sorry. We have the spring and the mass, and the mass is also put on the floor. When we draw free body diagram of the mass, we don't have the spring anymore, but we have the force done by the spring. We don't have the floor anymore, but we have the normal force. And we have the mg, or the gravity. Body force means the force that apply in the boundary of an object. For example, the gravity apply to all particles in the mass, and we can sum it and represent by the point force applied at the center of gravity. The surface force apply on the boundary or the contact point between the component and the surrounding. The surface force can be a point force or distribute force. In the real system, the normal force is distribute force that apply between the boundary of the mass and the floor. But in our study, many times, we assume the normal force to be a point force that apply beneath the mass. The spring force need to apply on a point that we connect the spring to the mass. And of course, the spring force gonna be a point force. Many times we have distribute force in the system, but we assume it to be a point force, like the normal force. Also, mg is the distribute force in the body, but we assume it to be a point force applied at the CG. It's just concept to make it clear. And we draw the free body diagram and we apply the conservation of momentum, linear, angular momentum to obtain the equation of motion. I will make it clear in our example for the conservation of momentum law. And before we have a break, maybe let's have this as we're gonna have 2 more slides before we have a break, okay? Variable in a system, variable in a system. To model system, to model any system, we need to define a set of variables to describe the system. And of course, we're gonna have the independent and dependent variable. Every time, most of the time for the vibration problem, the independent variable gonna be time. Independent variable gonna be time. And dependent variable gonna be the variable that change against time. For example, the displacement from equilibrium position. If you have a mass spring system, the displacement from equilibrium, time independent, the variable that dependent to the time is the displacement x, linear displacement x. How about the rotational system? Rotational system that vibrate back forth. We also have the theta that varying against time. So time is independent variable. The dependent variable can be the displacement from the equilibrium position in the vibration system. And coordinate. The coordinate in the system, if we see this system, how many coordinates that we can see in this system? How many coordinates that you see in this system? You can try to give an answer. We need volunteer. How many coordinates that we can see in this system?
2.
One more time. Okay, maybe 2 may be correct, 3 may be correct, but maybe in this slide, okay, let's go together. What we can see here is the coordinate x, describe the position of this block mass M1. The coordinate y, describe the position of M2. How about the theta? It describes the rotation. Of the pulley. And this pulley at the radius R2 is connected to M1. At the radius R1, it connects to M2. So actually, seeing by eye, it seems like we have 3 objects. We have mass M1, M2, and have the pulley. And we have 3 coordinates that describe the motion of M1, the motion of M2, and the rotation. Here are the coordinates. That seems to be possible, but seems like we have many constraints in this problem. I'm gonna give you the first constraint that I can see here. The first constraint is x equal to R2 theta. This is my first constraint. We need one volunteer to give the second constraint. Do you have any idea for the second constraint?
Y equal R1 theta.
Yes, thank you. Thank you. Y is equal to R1 theta. This gonna be true. This gonna be true. We need one assumption. The assumption is the cable cannot be shrinkable. The cable need to be like in tension, under the tension, and cannot be extend. The length cannot be, the cable is not deformed. So that when we pull the M1 with displacement X, the roller gonna rotate with the theta with this relationship. Okay, so in the beginning, we said that we have three coordinates: X, Y, and theta. And we have two constraints. Finally, in this problem, we have three coordinates that are independent. The three coordinates are independent. If we're not talking about the constraint, the three coordinates X, Y, and theta are describing the motion, the rotation of the pulley, the motion of the mass M1, M2. We have three coordinates without the geometric relationship. But when we consider the geometric relationship or the constraint equation, we have two constraint equations. Finally, the next keyword that we are going to talk about is the degree of freedom and the generalized coordinate. Do you think this system have how many degrees of freedom? How many degrees of freedom of this system? Do you have any idea? Can you answer one more time? I cannot hear you.
1.
Yes, thank you. So this system have 3 coordinates and have 2 constraints. We have 1 degree of freedom, and this 1 degree of freedom can be described by x or can be described by y or can be described by theta. If you say this system have 1 degree of freedom and it can describe by x, x can describe the motion of mass 1. X can describe the motion of mass 1. And by the geometric relationship or by the constraint, you can obtain theta if you know x. And by this constraint, if you know theta, you know y. So only 1 coordinate can describe the motion of the whole system. Only 1 coordinate can describe the motion of this system. So this system have 1 degree of freedom. The coordinate that we select, we call the generalized coordinate. We have 3 possible coordinates, x, y, or theta. But the one that we select, we call generalized coordinate. From now, we're gonna have many systems as examples. You need to answer how many degrees of freedom of that system and what is or what are the generalized coordinate of that system. For this system, you may answer, we have 1 degree of freedom in this system and coordinate x is a generalized coordinate. Or you may answer, hey, this system have 1 degree of freedom and coordinate y is a generalized coordinate. You can say like this also, because if you know y, you know theta, you know x. Or you can say that the theta is the generalized coordinate that you select. It's also correct for this. So, wow, sometimes I don't like myself. I always teach it before the slide explain. So, okay, take the slide as the conclusion. The degree of freedom is the number of independent variable that require to completely describe the motion of the system. And the generalized coordinate is the set of independent coordinate. Before this, we have 1 degree of freedom. So the set of n equal to 1 of independent coordinate, we can select x, can select y, or can select theta. So example here, from the previous slide, we know that degree of freedom, number of degree of freedom equal to 1. And the generalized coordinate can be x, or can be y, or can be theta, depend on what you select as a generalized coordinate. We are going to consider the second example. I will describe the example and we're gonna have the break. And I will give you a few more minutes to think about the degree of freedom of this system. In the first example, we have the constraint. We have the constraint here. X and theta have constraint. Y and theta has constraint. So finally, we have only one degree of freedom. But in this system, please take few more minutes to consider, do we have constraint? And how many degree of freedom for this? How many degree of freedom for this? And what are the generalized coordinate for this? How about 10 minutes for break?